So, today we will continue from what we were discussing yesterday. So, the application of mass transfer in the environment. One of the yesterday's and the last two classes we are looking at interfaces where there is a fluid. So, we look at now a case where there is a solid. So, specifically what we are interested in is this system where there is sediment. One is a solid phase, the other one is a fluid phase. So, it is sediment, water or soil, air systems. So, both of them are somewhat similar, but we will start with sediment water, which is a simpler system in terms of what happens. So, yesterday's class we looked at one example where there is a spillage of material. It chemical sinks down and lands on the surface of the sediment. So, these are what is called as dense NPTELs or dense non-aqueous phase liquids. So, these are abbreviations that are commonly used in the environmental jargon. So, NaPl is a non-aqueous phase liquid, can be anything, oils to insoluble chemicals. So, these are all things that will form a separate phase in water. So, things like many other chemicals are under this category. So, DNAPL is those chemicals which are dense, and then there are LNAPLs which are light. So, again as discussed earlier, the density is greater than density of water. Here the density is less than density of water. So, these are also called as sinkers, these are also called as floaters. As the name suggests, if there is a spill, the light NAPLs will float on water, and therefore their transport, fate and transport is different from that point of view. And the sinkers cause a different effect. They will sink and they will land on the sediment, and from there their fate and transport is from that context, from that point of view it is calculated. So, what happens to this sinkers? So, because this is at the interface of water and sediment. So, when it enters here, one of the things that does happen to the sinkers, one is evaporation, the dissolution starts taking place straight away. Water is flowing, it is going away, but it is also traveling inside because there is a gradient, it goes inside. So, how does it go inside? So, two mechanisms. One of the problems in this thing is that it will sink, but there is a sediment here, which means that it has to now, if it wants to displace the water, it has to go through these pores, and that is there is a lot of surface tension when it comes to the small pore. Then the water will not allow the material to just sink in nicely. It takes a lot of resistance, effort to do that, and therefore, many of these chemicals they find it difficult to get into, depending on the surface tension between these three systems, between the water, surface, the solid and the other chemical. It may not percolate into the sediment, it may just sit on top of the sediment. So, when that happens, then there is dissolution occurring based on the mass transfer rate that we looked at yesterday using Ka24, this equation. But it is also spreading downwards, and it spreads downwards mainly again by dissolution, not by percolation. So, it may happen, percolation may happen, but not necessarily. Okay, it may just spread by dissolution. So, two possibilities inside here. If percolation is possible, it will do percolation in porous medium. It is very hard because water, especially in the presence of pores, provides a lot of resistance for displacement. There is no place, buoyancy driven or density driven displacement, it is difficult for it to happen inside porous media. So, it requires a little bit of external energy for this to happen. So, sometimes it may not happen, it will just sit there, okay. And It's a surface depends on interfacial forces. The other possibility is, which will definitely happen, is dissolution and diffusion. Okay, into the sediment. So, over a period of time what can happen is you start with this big spill on the surface, and over a period of time this spill can spread. Over a period of time it can spread, and it spreads in this there is no chemical, there is no napple here, this spread, this is a plume. Again we are calling this a plume because it marks the boundary of the chemical concentration. It is just like the plume we have in the atmospheric dispersion, it is a boundary. Okay. Now here the boundary is, it is a plume of dissolved concentrations. The chemical is dissolving in the water and is diffusing slowly and it is spreading. So over a period of time at T1 you will find this, T2 you will find this, T3 you will find this, it is spreading out. So it will spread out in the manner that there is pure chemical here, it is spreading out, and pure chemical is also dissolving, right. So there may be a point of time in the future, say at some time T, let us call it T dash. So this all pure phase is dissolved, which means there is no more pure phase. So when this percolation is happening, it is also accumulating on the solid surface now. Okay. It is absorbing on the solid surface. So at that point in time the system will now look like this. There is water, and there is a large section of contaminated sediment that is sitting inside here. Okay. There is no pure chemical, all the pure chemical is gone, either pure chemical has gone into the water or gone into the sediment in this case. So this is the boundary of contaminated sediments, okay, at a different concentration. So you will find different concentrations at a function of height at the depth inside the system, and this is a contaminated sediment volume. So it takes a long time for this to happen. Okay. So at this time there is clean water that is coming, clean water is flowing. Okay. Now what happens? This contamination has happened over a period of time, water has been contamination, all the pure chemical that was here has gone away, and there is and this chemical is also spread here. Now this chemical will start going out. To reach this point it takes a long time because it is diffusion driven and the dissolution is a very slow process. So this is the reason why we call it as historically contaminated sediment, and these things have contaminated sites. When we invoke the word history, it means that it is very long back, it is a lot of time. Now we are saying 10 decades, 2 decades, 3 decades and all that. So and the consequence of that is that sometimes something may have been contaminated 30, 40 years back and it is still there and it is causing an effect now. So from the point of view of there is an aspect of liability, it is a complicated thing. So liability is who is responsible for this, somebody is responsible for this, so that whoever is responsible may not even exist right now, it is gone past. Some corporation has done this 20, 40 years back when there were no regulations, and now we have to deal with it. So this liability is a problem, and therefore what we should do about it in terms of cleaning up this site and all that then becomes a big issue. So there are a large number of scenarios in the world where this contaminated sediment is a big problem, because contaminated sediments is usually the contamination takes so long, it's very difficult for people to see that it's being dumped somewhere. So underwater you can't see, you think everything is fine. When will you see it? You will see it when there is a concentration in the water downstream and there are fish or something which are accumulating it. Yeah, concentration in any of these receptors is high, and if people do fishing and then they have a problem, and then they'll realize what is going on in this system here. So how does one, if there is a contaminated sediment site, how do you model this, the flux? We are interested in the flux at the surface. We are interested in Na32, sorry, Na23, the flux into water with an interface with the sediment. Okay. Now this flux is now, how do you define this flux? In the same way as we have defined the other systems so far. How do we define, write down this number Na23? There is a river flowing there. So we write Ka23, the mass transfer coefficient, multiplied by, we write two concentrations, one rho A2. Since we are writing a water side mass transfer coefficient, we write a water side concentration at z equals to 0 minus rho A2 infinity, which is whatever is the concentration coming, the background concentration in the river, in the water. And so there is some amount of flux that is coming here, this is going here, and so this concentration will be the combination of these two using the box model. Okay. This term we looked at yesterday's class, lot of correlations, you can take one of them and use it. What about this term? What will be this value rho A2 at z equals 0, which is z equals to 0 is this. We are defining z equals to 0 here, and z keeps going in this direction, increasing in the downward direction. So at z equals to 0 is the interface between sediment and water. The flux is defined there. This is the flux at z equals to 0 is defined as this. We are interested in this flux in the box model. So what is the nature of the flux and the rho A2 z equals 0? How do we estimate it? First question, is it a function of time, is it constant? Can you assume it is constant? No? Why? Because? It is diffusing into water. It is diffusing into the water, so it is going away. But if this goes away, something is coming from below, can replace it. So if you look at the process itself, if you look at the sediment water interface, we are looking at, let us say we are looking at this, I am expanded the view of this. This is the water, it's flowing. There is this molecules that are sitting here. This is in the water, this is pore water. This is where the diffusion is occurring, in the pore water. This is the solid. So from this point, this is z equals to 0. So from where here, and there are some, there is rho A2 infinity here, let us assume that is 0 for the time being. So there is a big driving force between this and this, there is a large number here and there is almost nothing here. So this is, and there is the Ka23, small Ka23 in this zone. So from here to here it takes the mass transfer coefficient and jumps into the water. Okay. what happens here in the zone that is between these two solids, what are the processes that are happening? So, because there is a gradient, some of these things go away into the water. Yeah. Then what happens here? There is a reduction. So, to begin with, when this happens, when these things move away into the water, what happens then? You are saying diffusion is occurring from here to here, this mass transfer is occurring from here to here through convective mass transfer. Then the amount here reduces, some of this material go away. What happens then? That drives material from here to here. What is the assumption in, you are saying that this will go here, which means at the beginning, what was the scenario? Why will this go from here to here now? Which means, if you are saying now there is a concentration gradient after some material has moved out, what does it mean in the beginning? It was in equilibrium. So, you are assuming equilibrium to begin with. This is really not a realistic scenario. Okay, there is no equilibrium in the beginning. The beginning is when things started. The chemical was dumped there, that is time t equals 0. So, it is never at equilibrium, it is always going in, we are saying it is going in and then it is coming out, all these things are happening. But for the purpose of our discussion, so this is very important, if you are going to model this mathematically, you need to make some assumptions. Okay. These assumptions are based on our whatever information we know about transport processes in the system here. Okay. So, if you assume equilibrium at t equals 0, we are also assuming equilibrium between the solid and the pore space. So, we are assuming that whatever is there in the pore space is in equilibrium with whatever is there on the solid. So, there is some amount sitting on the solid. This is sediment solid. Sediment solid is like, what is the equilibrium between sediment solids and the pore water? How do you describe the equilibrium between sediment? What is the description of this equilibrium between sediment solids and pore water? How do we define this? Yeah. How do we describe the equilibrium between solids, sediment and pore water? This K where this is the concentration in the sediment and this is the concentration in the pore water. In that system, this is the equilibrium that we are talking about. Okay. In the beginning, we are saying this is all in equilibrium and then it starts, driving force starts going in the reverse direction, in this direction. Okay. So, how do we write it? So, we are saying that over a period of time, what is one way in which, so in our equation when we are writing Na23 at z equals to 0 equals to Ka23 into rho A2 at z equals to 0 minus rho A2 infinity, which this equation we have written. The only way this flux is going to be constant is this is going to be constant. The only way this is going to be constant is this is rho A2 0, z equals 0, rho A2 at z equals 0 is this location here. This is going to be constant only if the rate at which it is getting out is equal to the rate at which stuff is being brought in. Yeah. For that, diffusion has to be of the same order of magnitude as what is going out in this case, right. Usually it is not true, because diffusion is a very slow process, material has to come out. Additionally, what is happening is material is not allowed to go out here. When material is lost from here, it is a non-equilibrium state. There is some initial concentration which is in equilibrium with the solid. The moment it leaves this equilibrium is disturbed. Yeah, so this is reduced, this concentration is reduced, which means that from the solids desorption will occur. Desorption will occur to replace whatever is there here, and then material from below, whatever is here, will then adsorb onto this. This equilibrium is disturbed, this equilibrium is disturbed, so on, all these things are happening, and then therefore there is a gradient that is always set up. The material from here cannot go and replace this, it is going here, then it is going here, all these things are happening. As a result, it usually, for us to keep this constant, depends on the relative rates of adsorption, desorption and diffusion. Because this process is faster than the rest. Mass transfer at the interface is happening at a much faster rate. The moment it appears there, it can get carried away, and then it has to wait for material to come. So what happens is these processes are slower, and therefore now it is slowing down slowly. So it is an unsteady state process. This is a function of time. At z equals 0 is really a function of time, and because this is a function of time, the flux also becomes a function of time. It is not a constant flux. It is only constant if material is being supplied to the surface as quickly as it is being taken away. That is steady state. This is unsteady state because it does not happen. So depletion occurs, as a result of which this lags behind, the supply of material to the surface lags behind this one. Okay. So accumulation is reverse accumulation, it is slowing down, material is not being brought in as quickly as it is being taken out. So it is unsteady state that way. So in order to model this system, we need to calculate what is the composition, what is the value of rho A2 at z equals to 0. So there we look at the system for modeling. So we take a control volume approach to this. So we take, again like the box model we do a box inside the sediment. So we take a box inside the sediment. This is the sediment interface. So we take a box inside the in which there are solids, and we are saying, and this is z and this is z plus delta z, and this is delta x and this is delta y.